Hello and welcome to today's tutor session of Class 11 Computer Science. We'll begin with the computer fundamentals, that is Chapter 1. Let's go ahead. First, we'll look at the evolution of computers. Now, the first computers that were built, they weren't exactly designed to perform a vast array of tasks. They were just used to make calculation process faster because the human errors that crept in while doing calculations were unacceptable. They just weren't fast enough and they made too many mistakes. Hence, for the first calculating device, the abacus was developed by the Mesopotamians back in 3000 BC. Now let's have a look at few of these devices that were used as the first computers. The abacus, which was developed in 3000 BC, around 3000 BC, it was also known as a counting frame, and it had multiple movable beads that sat on a beam. The frame itself is divided into two parts, and the numbers were calculated by the place value of digits of the numbers and positions of beads in between them. Now, we will not be going into an in-depth explanation of how the device works, as we have more important things to consider. So let's move on to the next slide. Napier's Locks and Bones, which was developed by John Napier in 1617, the device kicked off the idea of logarithms. Now, this device had multiplication tables embedded into the rods, and multiplication could be reduced to repeated addition and division to repeated subtraction. The even more advanced use of locks and bones could even extract square roots. Now, it is important to note that this was the device that kicked off the idea of logarithms, but the bones were not exactly the same as logarithms. Let's move on to the next one. The Pascaline, which was invented in 1642 by Blaise Pascal, this was one of the first mechanical computers to be given birth to. This used actually pulleys and rods and levers to move around the cylinders that we see in the white here. This was especially successful because it had a carryover mechanism. Now, we have all used this in everyday math life, but we'll just have a quick demo. Let's add 11 plus 29. Don't mind my handwriting. I'm more used to a pen or a pencil, not a mouse. So we'll have a 0 here, 9 plus 1, that's 10. We'll carry over a 1 here, so we get 1 plus 1, that is 4. So we get 40. Now this is the carryover mechanism. Now back in the day, this machine was exactly capable of carrying over numbers just like this. That is what made it extra effective. Now let's move on to the next slide. This machine is the Leibniz calculator. In 1673, Gottfried Leibniz worked upon the Pascaline, and the former Pascaline, this was an extended version of the Pascaline. The former Pascaline, which was developed by Blaise Pascal, was not capable of multiplication and division. So Gottfried Leibniz worked upon the machine, and now we have a Pascaline for extended version which is also capable of division and multiplication. The Jacquard Loom, this was one of the first machines to use punch cards to control beams. Now, punch cards are one of the first means to program a computer. They are basically cards with holes on them. The holes represent a 0, and the place where there are no holes, they represent a 1, which was the binary system. These were used to control the beams, and the concept of storing and retrieving information was born. This was one of the first computers to store and actually retrieve the information as the need demands. Now, to look at the contribution of the father of computers, that is Charles Babbage, the difference engine created by him was an automatical mechanical calculator. It could calculate various mathematical functions, do polynomial evaluation by finite differences, and theoretically could also solve differential equations. The analytical engine, however, was considered one of the first general-purpose computers. It was designed in the 19th century, and it was fully program controlled, and it was a digital computer, the first digital computers. This is the Mark I by Professor Howard Aiken in collaboration with IBM. That is the International Business Machine. The first electromechanical computer was born in 1944. It could multiply 10-digit numbers with 5 seconds. That is two 10-digit numbers with within 5 seconds, and that is to be considered. Now when we think about the modern day computers, it won't even take a fraction of the second. So it used the analytical engine as the base and the foundation for it to be built upon, and this was the first computer that could execute code without any human intervention whatsoever. Now let's have a look at the architecture of computers. The first one is von Neumann Architecture, also known as the Princeton Architecture. Now this is a really important concept in computing, so let's pay attention. It was first proposed by Dr. John von Neumann in 1945. The concept of a stored program computer was born. Now, by stored program computer, we mean that the instructions or the program was actually stored on board, which was a magnetic reel or some form of magnetic storage. This was also known as the Princeton Architecture. Now, what the computer basically did was, it would fetch an instruction or a data, not both at the same time, emphasis on that. It would fetch either the data or the instruction, and then it would read the instruction, which would tell the computer what to do with the data. This had a limitation, that was to bring the data to the processor, there was only one single channel. By channel, we mean that it was a pathway for the data to travel. So we could either fetch the data or the instruction at a single time. We could not do both. This was known as the John von Neumann bottleneck. ECVAC was the first stored program computer in the world, which was built in 1952. This here is a pictorial representation or a schematic representation of von Neumann architecture. We can see that the input goes into the CPU, that is this part, which would comprise of the control unit and the ALU, that is the arithmetic logic unit. Now what we need to focus on is that there is only one single channel here, this part. Okay, so the problem was that there is only one single pathway for the data, so you could either fetch the instruction or you could fetch the data from the memory unit, that is this part. Now that being said, I hope it's clear that the von Neumann architecture had one major flaw, that was it was limited to either fetching the instruction or either fetching the data at a single time, which would often decrease the speed of the computer. So, and finally, after all the processing, what we get is an output. Now let's have a look at the generation of computers. This was classified on the basis of different stages of development, and the computers that we use today are from 4th generation, which we'll encounter in the coming slides. Now first let's look at the first generation, which was from 1942 to 1955. The first computers to store program was classified into the first generation. They were characterized by vacuum tubes. Vacuum tubes, they were basically glass tubes which were used to control and amplify electronic signals. When they worked similar to transistors, not exactly like transistors, they generated a lot of heat and would require often a lot of maintenance. They were unreliable and they need to be continuously cooled. The first program, they were programmed in machine level language, and the first computers to run on vacuum tubes were the ENIAC, UNIVAC 1 and EDVAC. Let's have a look at the second generation of computers. Moving on to the second generation of computers, which was from 1955 to 1964. They were based on transistors and magnetic core memory. Now what are transistors? Transistors are they're basically semiconductor devices which are used to amplify and modulate electric signals. They were basically just a really small version of vacuum tubes. They too did run on some form of electricity, well, if you know what that reference is for. Now these are integrated chips, that is the third generation, which went on from 1964 till 1975.
The basic idea was to make your whole electronic circuit a whole lot smaller. So they would put different components of different electric components, that is resistors, transistors and capacitors, into a really small silicon chip, and they would represent, or they would function as a whole electronic computer, and they would function as a full-sized electronic circuit, which primarily used up a whole lot of space. So they generated a lot less heat and consumed less electricity. The computers were smaller and faster, which also resulted in a more reliable computer. The prolific computers, which we see in the example, is the Honeywell 6000 series and the IBM 360 series. Just a short note on IC, they are just a flat piece of highly purified silicon that can hold anywhere from 100 to a million electronic components that would otherwise take up a lot of space on a normal PCB. So let's go have a look at the fourth generation of computers. We will just skip through here. You can always pause the video. We will move with a bit of pace, and because we have time constraints, so you can always pause the video and rerun it if you feel like the speed is getting a bit too much. My apologies for that. The fourth generation of computers, which consisted of integration of a complete CPU into a single IC. This was first achieved in 1971 and was named microprocessor. This marked the beginning of the fourth generation, that is from 1917 to till where we are right now. I'm sorry, from 1975 to till where we are right now. The ICs that came with LSI and VLSI technology. Now, LSI is large scale integration, which is just a measure of how many components you can put into a single microcontroller, and the VLSI is very large scale integration. That is another yet a bit bigger measure of how many components you can stuff into a controller. The microprocessors were developed and portable computers became popular, as did network and data communication. Now these computers were really reliable and powerful, but still really compact and small in size. The computer consumed a whole lot less energy and did not exactly need air conditioning and all those to run. The production costs also dropped, which made it more affordable to the average man. Let's go ahead and look at the fifth generation of computers. Now, coming to fifth generation of computers, they are still under development, and hopefully they'll utilize the following concepts in the future. That is parallel processing, superconductivity, and artificial intelligence. Parallel processing is basically you put together a whole lot of microprocessors, then you divide a really big task into many small ones, and you supply each microprocessor with a smaller task, so they do all their work and we can finally combine the result. This would increase the efficiency and as well as the computing time that would take usually a single computer a lot of time, and the parallel processing would hopefully decrease that. Then next, it's basically a divide and conquer mechanism. You divide the whole task into smaller ones and then get microcontrollers working on smaller tasks. That's pretty much it. Now, superconductivity, it's a physics phenomena. Superconductivity is when a wire that we use to conduct electricity is basically comes out with zero resistance. That is, energy loss is zero in a way. As of now, we do not have that kind of mechanism, which, I mean, those wires require really low temperatures to run on, and currently none of the elements are capable of delivering zero resistance at room temperature. So currently that is not viable, but it is still under development. The third is artificial intelligence. Now, artificial intelligence, we do use a form of artificial intelligence in today's modern day computing, like speech recognition or the opponents that we face in the games, but they are not exactly true artificial intelligence. They are more of already thought computer programs. Even though they are named as AI, they do not actually, they technically qualify as AI, but they do not actually form the true AI. That would be the word. So that is it about the fifth generation. As it is still under development, we don't have much to speak on. Now let's have a look at the basic working of a computer, that is the functional components of a computer. See, every computer is basically a lot of hardware and a lot of software that work together to give us the desired output, whatever we want in the end. Now the data that we have, we input that through the input unit. The input unit would pass that on to the CPU. The CPU would then temporarily store it in the memory that is here. Then the data and the instruction that would be fetched would move to the ALU. This process, the fetching of the data, would be controlled by the CU, that is the control unit. And if, let's just say, this is the data that we have fetched, the ALU would work on the data, then it would provide the output, which would be sent to the output unit here. Then the output unit would convert the computer language into whatever language that was understandable, that would be understandable by a human. So that's what the output unit does. Now to talk about this part here, the registers, memory registers are, they basically, they are data, they store data, but they don't actually store the data that we input. They store the address of the data. So each part of data or each component of data is actually recognized by its address. So these memory registers would store in addresses here, the address of the data that we want, that which we would have to access, or the data which we would have to work upon. So that's what the register is for. So in a nutshell, really quick, the input unit would take in data which would pass on to the CPU. The CPU would store it in the memory, and the memory would allow the data to be passed on to the ALU, which would be controlled by the CU. The ALU would work upon the data and then put it out to the output unit to be presented in some form that would be readable by a human. That's pretty much it. That's how a basic computer works in a nutshell, that is. Now let's have a deeper look. First, let's have a look at the input unit. This was basically any input device which we have learned in class 6 or 7. That would be the mouse or the keyboard or webcam or all those. They were, if it was capable of converting the human data into some form that would be understandable by the machine, then that would be considered as an input device. The central processing unit, which is next, this we all have known as the brain of the computer in lower classes. So it comes with three major subcomponents, that would be the ALU, the CU, and the memory registers, which we have seen in the previous slide. So that being said, let's have a look at what the ALU does. The ALU, that performs arithmetic operations on the data based on instructions, as well as taking logical decisions. So in a nutshell, this part of the computer is what works upon the data that you provide in. It would read the instruction, then it would know what to do with the data, then it would execute the instruction, and then it would put out the output. After that, we have the control unit. Control unit is what controls the flow of data, what is to be sent where. Those decisions are taken by the control unit. The memory registers, as we said, memory registers do not store the actual data, but they store an address to the data. Now each one of us human beings, we have an address where we stay. Exactly like that, data too has an address where they reside. So in order to recognize the data, they need an address. These memory registers are those that store those addresses. I hope those are clear. Now let's have a look at the memory of the computer. The memory, we don't need much explanation. We know what a memory is. Memory is something that stores the data. Now we have two types of data: the data which may be permanent, which we need to store for future purposes, or the data which is temporary, which we need to execute certain instructions for. Let's have a look at the two types of memory. The first one being the primary memory. Primary memory refers to the RAM, which is random access memory. This is a form of volatile memory, and they are also called volatile memory. It stores the data and instruction for the current task. It does not hold any data that is permanent, and as soon as you cut the supply to the RAM module, the data is lost. The RAM takes in data which is needed to complete the current task. It completes the current task and then it frees the space. That is why it's called a volatile memory, because it does not last there forever. It only holds the data as long as it has the need for it, or as long as it has the power. Talking about the secondary memory refers to anything like the pen drive or the hard disk or the solid state drive, which is used to store the data for future purposes. Now this does not depend on the power provided to it. It will, once the data is written to it, it will retain the data regardless of the power which is supplied to it. Now finally, coming into the output unit. The output unit consists of devices that are capable of converting the data which could be understood by the machine to a form that could be understood by the humans, which was basically the output, the monitors, speakers, printers, etc. Anything that could make us understand what's going on inside the computer is output unit. That's a weird analogy, but don't mind. Now in the next topic, we discuss how the various components of a computer, they talk to each other or they communicate. Now this communication was done by using bus. Bus doesn't stand for anything, but it was just a term to describe a pathway. Now these buses were used to send data to and fro various components of a computer, which were in the early computer eras they were wires, and now we have they were pretty much wires, that's it. And so we have to discuss about the common bus architecture, which is almost everywhere these days. I mean, except for the supercomputers that require a very large amount of speed. The common household devices, they all pretty much use common bus architecture. Now the common bus architecture is what we see here. This was the common bus architecture, in which they had a common bus here. That was this part, this one, and they had sub buses. There was these, and this. The common bus architecture had three main components, which was the address bus. Now the address bus was used to carry the addresses of data, as we have discussed in the previous slides. Each part of data has a basic address associated to it. Now the address bus was used to carry around the address location of the data or the instruction. Now second, we have the data bus. This was actually And sorry, this was used to carry the actual data or the actual instruction that had to be moved around. Now the control bus, they carry the commands from the microcontroller to various components of the computer. So the microcontroller is what, in the modern day, the microcontroller is what tells various components of the PC what to do. So they have to speak to each other. Now the control bus was used to transport the commands from the microcontroller to the various components. That was all for the common bus architecture. Now let's talk about the concept of booting. Now booting was the process of loading the whole OS and whatever proprietary drivers that were used to run a system, that are actually needed to run a system, were loaded into the RAM. So let's have a walk through the basic steps of BIOS. So when you switch on a computer, the first BIOS, that is the basic input output service, first performs a post check, that is the power on self test, that checks the various components of the computer. Now if a post test fails, the computer often just displays an error message. The post check is what checks for the RAM, the ROM, the OS, the USB ports, not exactly USB ports, but the other crucial components of the computer that actually are necessary for the smooth functioning of the computer. Once the check returns true without any errors, the BIOS checks the CMOS to look for a boot record. Now, what is a boot record? The boot record, or the master boot record, it was a special type of boot sector. Boot sector meaning it was just a partition in your hard drive or in your flash drive that would come at the very first of the hard drive. I mean, the hard drive think of it as a long bookshelf, and the first shelf was occupied by this boot record. This master boot record, or just the boot record, would store information about the various files on that, and would also have a bootloader in it. The bootloader is basically it's a program that you can execute that would load the necessary files into the RAM, the necessary OS files into the RAM. The bootloader also holds the information about where the bootable OS exists. And after that, after the basic files of the OS are loaded into the RAM and are executed, the control that was formerly held by the BIOS, that is the basic input output system, would be transferred to the OS, and then the OS would take control of the booting process, and after that the OS would select the necessary drivers and softwares that are required to run the computer and then load them into the RAM. Now let's have a quick run back of the concept of booting in short steps. First, that would be when the BIOS gets power, it runs a post check. After the post check returns true, the BIOS searches for a bootable OS on the drive. Then the BIOS executes the bootloader, and after that the BIOS loads the OS into the RAM. Then the control is taken over by the OS. So that was it for today's tutor session, and that was the first chapter of Class 11 Computer Science, Computer Fundamentals. Now I sincerely hope all of you have a clear-cut understanding of all the topics that were taught in this session. If not, feel free to reach out to me with any doubts, queries or suggestions in the email address provided in the final slide. That is siddu89@gmail.com, and I would be open to all kinds of suggestions. Try my best to improve in the upcoming sessions. Thank you, all of you.